Test 1, 2, 3, 4, 5. Hello.
हाँ ভাইস প্রিন্সিপাল স্যার এসে গেছেন ভাইস প্রিন্সিপাল স্যার এসে গেছেন আচ্ছা কালোবরণ এসেছো কালোবরণ হ্যালো ভাইস প্রিন্সিপাল স্যার এসে গেছেন প্লিজ টার্ন অফ ইওর ক্যামেরা ভাইস প্রিন্সিপাল স্যার এসে গেছেন
I have joined.
ওকে স্যার থ্যাংক ইউ স্যার
Just 1 minute.
Please tell me when I have to begin.
ওকে ওকে ম্যাম
Good morning, Orpita Di.
Good morning, good morning.
114 so far joined. 114, I see.
ইয়েস
Has the speaker joined?
I don't think so.
he will join at 10:45 a.m.
It's almost time.
Yes yes
Meanwhile, while we are waiting, very good morning to all the participants, all of us who are present here from across the country. Greetings from Scottish Church College.
Thank you, ma'am.
Start.
A very good morning to Dr. Urpita Mukherjee, our principal, Scottish Church College, Dr. Supratim Das, our vice principal, sir, Scottish Church College, Dr. Samrat Bhattacharya, IQAC coordinator, Scottish Church College, dear colleagues and the registered participants all over India from different colleges, universities, research institutes, and IITs. We have amongst us some of our ex-teachers of the department and notable alumni. A special thank to the speaker, Professor Kalobaran Maiti from Tata Institute of Fundamental Research, India. He is a well-known, famous experimentalist in condensed matter physics. On behalf of the Department of Physics, Scottish Church College, I welcome you all to this webinar, Electron Spectroscopy and Undergraduate View. This is the first webinar of our department, and we are very happy to announce that the registered participants in this webinar has crossed 1,000. Actually, the figure is 1,058. This is a huge number for us, and we will be able to reach to all the participants through the technological support of virtual reality. We hope it will be a grand success for us. On this occasion, I request our principal ma'am, Dr. Urpita Mukherjee, to say a few words. Ma'am, please.
Thank you, Dr. Nandi. Respected speaker, Professor Kalobaran Maiti, Dean Natural Science Faculty, Tata Institute of Fundamental Research, Mumbai, Dr. Supratim Das, Vice Principal of our college, Dr. Samrat Bhattacharya, IQAC Coordinator, Dr. Upendranath Nandi, Head, Department of Physics, other dignitaries present in this webinar, dear friends, colleagues, and my dear students, I welcome you all to this webinar on electron spectroscopy, an undergraduate view. I would first like to congratulate the Department of Physics for organizing seminars from time to time on topics related to Calcutta University undergraduate physics syllabus. This time it's a virtual meeting on account of the ongoing pandemic, but this has enabled us to include many more participants. As you've already heard, over 1,000 participants from across the country. Generally, we have about 170. That's all we can accommodate in our seminar hall. Organizing extension lectures is one among many good practices of this college. We always encourage programs that help our students' knowledge grow beyond the boundaries of their textbooks and arouse their interest in research. They learn to analyze and think independently and also learn the art of presenting original thoughts to a learned gathering at a seminar. I'm not a physicist, so I will not dare to tread on unknown, unfamiliar grounds. Hence, without taking up more time, I should pass on the screen to the next speaker. I hope that the discussions held in the course of the lectures today will not only benefit the students in their preparations for university examinations, but will also inspire them to pursue higher studies and dream of becoming outstanding scientists someday. I welcome you all once again, and I wish this webinar a great success. Thank you.
Thank you, ma'am, for encouraging us and welcoming all the participants. Now, I request our Vice Principal, Sir, Dr. Supratim Das, to say a few words on this occasion. Sir, please.
Yes. A very good morning. I think I am audible.
Yes, sir. Yes, sir.
A very good morning to all of you. Today's distinguished speaker, a very eminent physicist, Professor Kalobaran Maiti, our principal ma'am, Dr. Orpita Mukherjee, the IQAC coordinator, Dr. Samrat Bhattacharya, head of the department, physics, Dr. Upendranath Nandi, all the viewers, all the participants, and my senior colleagues in the Department of Physics. I particularly would like to congratulate the department for organizing this kind of a webinar on electron spectroscopy and undergraduate view. It is true, as the principal said, my knowledge about this particular theme is absolutely nothing. But as a social scientist, I'm familiar with a basic fact that very eminent stalwarts like Heinrich Hertz, Max Planck, or Einstein, their names are very much associated with this particular field of work. So that way, I'm grateful to the department for organizing this webinar. It is true that we are in the midst of a very terrible mounting global COVID-19 pandemic. And every day we hear that the pandemic is actually robbing us of everything. Maybe that is true. But there is a silver line. This kind of webinars. Suppose in the normal situation, it would have been impossible to get Professor Maiti in Scottish Church College for giving this lecture. As this is online, so we can hear him today from Bombay. Maybe that tomorrow there will be speakers in many such webinars, maybe from London, maybe from even New York or any other major cities which are affected by the pandemic all over the globe. So that is definitely a silver line. And what should we actually deserve? What should we do? We should fight back. We should fight back. Civilization has seen innumerable number of crises in the last 1,000 years or 2,000 years. Every time civilization has, it had its triumph. So this time also that we are amidst pandemic, we are organizing this webinar. That is a very great thing that we are fighting, and that there is a spirit among the youth, among the students, among others, that that is the spirit which is really required, which is badly required. The spirit, we should be charged up, and particularly we know that because of the pandemic, everything has been badly affected all over the world. But I would particularly refer to academia, global academia. Things will no longer be the same in the days to come. This pandemic is going to tail upon the global academia in future. But so what? We will carry on. We will go ahead. And this seminar, or this kind of seminar, online seminars, should be taken as the silver light at the end of the tunnel. I wish every success of this webinar. Thank you very much.
Thank you, sir, for your very encouraging lecture and support to the Department of Physics. Now, we are going to introduce today our speaker, Professor Kalobaran Maiti. It is not a hard task for me because I know him from my class 11. We stayed together in a hostel of Ramakrishna Mission. Professor Maiti did his BSc from Presidency College. Then it was a college, not university. Then masters from the University of Calcutta. Then doctorate from IIC Bangalore. Then he went abroad for postdoc, for doing postdoc. Mainly he was in Germany in several institutes, particularly in Dresden. Then it's a huge biodata for him, long list there. At present, he is the Dean, Faculty of Sciences at TIFR. He has got several prizes. PK Iyengar model, latest one, I think. Then Humboldt Fellowship, Shanti Swarup Bhatnagar Award, the Indian Nobel, as you know. He's a great experimentalist. Particularly, he works on the topological insulators, on the surface properties, carrying out experiments. Now, he's doing a very great job in that particular field, just measuring various physical properties of diluted magnetic semiconductors and oil semimetals, which is a three-dimensional analog of graphene. Professor Maiti is a very well-known experimental physicist in condensed matter physics in India and abroad. Now I request Professor Maiti to present his work for the students in electron spectroscopy and undergraduate view. Professor Maiti, please.
Okay, so can you hear me?
Yes.
Okay, so first of all, I like to thank Professor Upendranath Maiti and colleagues at Scottish Church for your kind invitation. I always really enjoy talking to students and interact with people, but often it becomes difficult to travel because of various administration and also activities in the lab. So now, as the principal and vice principal mentioned, that because of this travel restriction, it has become easier to interact with people via web. Although I personally feel that one-to-one interaction is really very good and much more enlightening. So today I will try to give a brief overview about the electron spectroscopy. So normally, you know that this is a technique where one needs to really go into the deep physics and underlying behind various electronic properties. But I have decided, because it's a talk to the undergraduate students, so I thought that I'll give a brief overview about the technique and how it can be used to understand various properties. Just a overview. So I'll try to discuss few interesting properties or puzzles, how these can be solved using this kind of technique. So if you have any question or anything, you can stop me at any point. However, I don't know how it will work. Normally, one-to-one discussion actually is very helpful for that. But I hope through web we'll be able to do this. So before I go into the subject, I like to acknowledge all my group members, so who has been contributing over the years on this activity. So these are the alumni of my group. So many people, they have completed their PhD and they are now doing some job somewhere in India or doing postdoc abroad. There are several postdocs who has also contributed significantly. there are junior and senior research fellow. So this is a stream which TIFR has. So the students, they are not registered for PhD at TIFR because they could not pass through the entrance test, but still can do their research as a junior research fellow or senior research fellow. So, and they can be registered elsewhere. So this, sometimes we have students of that kind. So, quite a few are there in my group. So they have now finished their PhD. So at different places outside. So this is basically the present group where I have 3 students doing PhD here and 1 in University of Slovenia, so University of Nova Gorica, and 2 postdocs and a scientific assistant, scientific officer basically, who takes care of the lab. So this is basically the manpower who has been, they're really very bright and contributing actively in the activity, which has helped significantly to have this activity functioning well. As you know, I just want to give a brief overview about the photoelectron spectroscopy or photoemission spectroscopy. As you know that, those who have studied photoelectric effect, so if you shine light on a material, so the light will be absorbed by electrons or the other excitations which is there. The photoelectric effect essentially says that the electron which absorb this light, if the energy of this light is good enough, then the electron can come out of the material. So then they come out, and so that is called the photo emission. So because you are emitting electron from a material by applying or by the excitation of the incident photon. Okay. So all this technique or experimental technique that I am going to describe is basically based on this photoelectric effect. So this slide I'll try to spend a little bit of time. So if you have, I hope all of you are able to see this slide. So you have a beam of photons, they are falling on the sample, which will be absorbed by electrons in a material. Of course, if the energy is very, very high, then you can also influence the excitations in nucleus and so on. But we are not in that high energy region. So our energy is basically the ultraviolet ray or say X-rays or hard X-ray of that kind. So where only the electrons can be excited, but the other part of the material remains in its initial state. Of course, you can have some kind of excitation, but you don't be able to. So now, light falls on this material, electron will absorb this light, and if the energy is good enough, it will come out of the material. And you put a detector which looks like this. It's kind of a hemisphere with some lens. Can you see the cursor? Can you please tell me? I don't know how to use cursor in Google Meet. Yeah. Maybe, Upendra, can you just tell me if you are able to see the cursor?
Hello? Hello?
Yeah.
শোনা যাচ্ছে? কার্সারটা দেখতে পাচ্ছি you can make it full screen. Is it possible?
Yeah, it is full screen only.
Oh, okay. I can see the cursor, no problem.
Okay, and it's not full screen?
Not full screen. Actually, it can be extended.
Okay, let me check. Is it okay now?
No.
No, it should.
Rather?
We'll let it continue like this because it's. Yeah, now it's okay.
Is it okay?
No, it was okay, but it went back.
I see, okay. I don't know how, let me check.
Just a minute ago, it was okay.
Oh. Just one moment.
Yeah, now it is fine.
Now it's fine? But
it is not,
it's not.
presentation mode, unfortunately.
I'll try.
Once you go to the presentation mode, something is happening. The next slide is also showing side by side.
Now it's okay.
It has gone back to the same position.
Okay.
But I think you continue in the slideshow mode, otherwise the animations won't come.
Okay, I think I'll do.
Yeah, please go back to the slideshow mode.
Yeah. Now it's okay.
Yes, okay.
Yes,
Now
sir,
it is
yeah,
okay.
it's fine.
Okay.
It is okay. That's fine, perfectly fine.
Okay. So I'll just. Okay, I'll get the cursor. Now you can see the pointer.
Yes, yes.
Okay, so so you have some light falling on the sample, and this light will be absorbed by the electrons, and the energy regime, as I said, that we work, which is ranging from say ultraviolet energy to the hard X-rays, so which is something like a few electron volt, like 5 to 6 electron volt to say 10 kilo electron volt. That so in this range, only the electrons will be sensitive in a material to this kind of light. So now, as you know, that the work function, that's the minimum energy required to emit an electron from a material, is of the order of 4 electron volt or so. So any light energy which is higher than that will be able to knock out electrons from the material. So that's the thing which happens in case of photoelectric effect. So now the light is absorbed and the electron gets emitted, and you put a detector which looks like this hemisphere, and there is a lens system. So the electron goes into the detector and we detect how many electron comes at a particular energy. This is basically the technique. So if you look at the energy diagram, so that looks like this, that this is your initial state. So for example, you have a 4 electron like say oxygen or say iron. So you have the 4 levels, and this is the valence band, which is the highest occupied energy band in a solid. And the Fermi level is mentioned by epsilon F, EF, which is the highest occupied energy level. So the electrons are occupied up to that. Above that energy, all the levels are unoccupied. So that's the unoccupied part of the electronic structure, or you can call it a conduction. Now, if this light is absorbed by electron in any of these levels, so their energy will be lifted. So by h nu, which is the incident photon beam. Now you can see that this EV is the vacuum level. So that's the energy difference between the highest occupied level and the vacuum level when the electron becomes free of the solid, so which is of the order of say 4 electron volt or so. So any energy which is there above this vacuum level will come out as a kinetic energy of the electrons, and you detect the electron which has energy in this range. Okay? So if you have a valence electron excited by h nu, it goes here. If you have a core electron excited by h nu, it goes here. And you can see that any energy which is above this vacuum level actually enables electron to come out of the system, and we detect by these detectors. Okay. Now, as you can see that this is a quantum mechanical process, because you are exciting an electron from one state, initial state, to the final state. So all the rules associated to this kind of transition will be applicable. So now let's go one by one. The number of electrons that we detect by these detectors, it depends on what. So if I call the intensity, that means the number of electrons collected at an energy epsilon, I try to present it in a way that even if you are not in physics, like doing chemistry or biology or other subjects, I hope anybody has studied photoelectric effect would be able to follow it and do some kind of an experiment. So I'll try to go in that level. So if you have any problem, you please interrupt and ask questions. So if the intensity is essentially the number of electrons that is detected at an energy epsilon. So this depends on the first quantity is called the photo emission or photo excitation cross section, sigma epsilon. This is basically the transition probability of an electron from its initial or ground state to the excited state. The next quantity is called the resolution function. So any experiment that you do, it's not perfect. I mean, any instrument that you design, you know that there are error bars associated. So the error can be higher or lower depending on how well you have made your instrument. But there are error bars. So there is a distribution of energy that goes into your detector. Like if you want to detect an electron of say 10 electron volt, you will always find that electrons of 9 or 10.1 electron volt also goes and hits the detector because your detector may not be that much. So this kind of distribution is basically looks like a Gaussian, so which is the resolution function. Then the next part is called the Lorentzian broadening. So this L, so that comes from the lifetime. So here the quantum mechanics is very important. You know that when you excite an electron from one initial state to the final state, so that initial state where electron was there, that becomes empty. Okay? And you have occupied a empty level which was there above the Fermi level. Okay? So now this empty state, which is called the whole state, it will not survive for long because there are many electrons above this energy level. They can jump into it and destroy this. Similarly, the electron that you have excited at the unoccupied level, that will not survive for long because there are empty states below that level where it can jump into it. Okay, so now you can see that as long as the hole or the electron, both which are there, you can implement this conservation rule like energy conservation, momentum conservation associated with the transition. But if the hole is destroyed, then of course this conservation law will not be applicable because something else has happened into this event. So this kind of effect comes also into the picture when you are detecting electrons, and the function usually looks like a Lorentzian function. This, if you have studied a transition of an electron from initial state to the final state, you will see that the transition probability always gives in the denominator some energy function which looks like a Lorentzian. So that way, so this intensity is valid as long as the hole is surviving and also the electron is surviving in the final state. So this lifetime comes as a broadening in your spectrum. Now the other term, which is exponential term, e to the power minus x over lambda. So lambda is called the escape depth. It's also, I'll tell you its importance in the photoemission spectrum. So when you excite an electron, the photons are falling on the sample. It can go anywhere. It can penetrate into the material. And wherever the photon is getting absorbed by an electron, so you excite an electron at that location. Now, electrons are excited at different locations in the material cannot come out because when they're coming out, it can experience various inelastic scattering. Okay? So if it's scattered, then it loses its energy. Then the energy conservation or various other laws that we are implementing, that will not be applicable. So then this kind of electron actually contributes as a background. So whenever you do an experiment, you will see that there is a huge amount of background that comes because the excited electrons actually are losing energies because of various loss processes. So the probability of electrons that comes out of the material, it's like an absorption experiment. So X is the depth at which you are exciting an electron. Lambda is the effective escape depth of the electron. So the number of electrons that comes out without undergoing any kind of scattering is actually proportional to e to the power minus x over lambda. And then that comes as the density of states, which is called TOS. That means how many electrons are there at that energy level from where you are exciting an electron. So you can see our intention is basically by this experiment, we want to determine how many electrons are there at a particular energy level so that you can actually get a microscopic picture of the energy landscape in a material. So that gives you an understanding about the properties. But you are actually getting influenced by various other factors in addition to the density of states that you are measuring. Okay? So this we have to keep in mind. So slowly I'll try to tell you how this influences before I get into any of the examples. But one thing that you can keep in mind that this technique, the photoemissions technique, where you are exciting an electron from an initial state to the final state, it's an extremely fast process. Means that when the electron absorbs a photon and gets excited, the time scale is of the order of some attosecond, 10 raised to minus 18 seconds. It's extremely fast. Any other processes like lattice vibrations or various other effects that you see, these happens of the order of say nanosecond, picosecond, or say femtosecond at the most, like electron-electron scattering. But when you are detecting by photoemission process, so that actually happens much, much faster. That means that when you are exciting an electron from a material, you basically don't allow the system to relax. So you basically are taking a snapshot of the electronic structure. So this is a very important aspect. So it means that if you are exciting an electron from one side, the system does not have enough time to respond to that kind of perturbation that you have created. So before excitation, whatever the picture that you had, somehow the response that you get actually represents that kind of situation. So it's more like taking a photograph when you are, although our body has different kind of effects, but you can actually get a posture by using a photo, making a snapshot if it is fast enough. Okay. Now let's go to the next aspect. Now I'll talk about this photoemission intensity a little bit more in details, and then how it can be used for various effects. So this is the expression that I have wrote just now. First of all, let's talk about the transition probability. Just now that I have talked about it. So the photoemission process. This sigma E, that is the transition probability, it depends on this kind of object. Don't worry about the details of this if you don't know. Anybody who has studied quantum mechanics, of course, know about it. But if you don't know, it doesn't matter. It's not necessary to know. So I'll tell you what exactly happening here. So this psi I is the initial state of the electron from which you are exciting, and psi F is the final state, like where you have excited the electron, and A dot E is the dipole operator. So basically, this transition probability depends on this kind of object, where you have an initial state, where you have a final state, and their hybridization, kind of an hybridization, and you take square of it. And this is a Dirac delta function, which ensures energy conservation. Epsilon I is the initial state energy, epsilon F is the final state energy, h nu is the photon energy. So that means that if the energy difference between the initial state and final state is equal to the photon energy, then this is 1, otherwise it's 0. So that actually is the conservation that we talk about. So the transition probability actually is depend on this initial state and final state, their hybridization, and it is applicable only when the energy difference is equal to the h nu. So various conservation rules, what it says, that h nu has to be the energy difference between the two states. Now, if epsilon b is the binding energy, so if the electron that we are exciting from a state has a binding energy of this, and this is the work function, so the remaining part of the energy will be used as the kinetic energy of the electron. So you can add them together which will give you the total energy of the photon that you have used to excite. Okay, and you know that energy is conserved in any process, whether you have a classical or quantum mechanical process that we talk about. Always energy is conserved. Means before the event, whatever energy was there, after the event, energy is same. Unless you really have an event where the energy that you measure is actually not the true final state energy, there are some other loss is happening. So this often you talk about in thermodynamics and so on, but in any process, always energy is conserved. So now what you know is that you know the photon that you have used, the photon energy. Now I somehow can determine the work function of a material, and this epsilon kinetic energy that we find out from our experiment. So if we know this object, we know this, so we can determine the bending. So that's the thing that we do in our experiment. The next is the momentum conservation. As you know, that in any collision or any kind of event, the momentum also is conserved. So any process that you have. So that means the initial momentum and final state momentum is same. So this is used extensively to find out the electron momentum when it was there at a distance. I'll tell you a little bit more about this later. And then the spin is conserved. You know that electron also has a spin, up spin or down spin, which gives the magnetic moment. Now, when you are exciting an electron from one state to the other, since the photon has an integer spin, like so it cannot really change the spin state of the electron. So the spin also is conserved. And then the other part is the symmetry, like mirror symmetry, rotational symmetry in solid. So you can see that when an electron is there in a material, there are four objects which are important. One is the kinetic energy or the binding energy of the electron. Another is momentum, another is spin, and the symmetry. These are the four quantum numbers. As we know that in an atom, you can define the electronic structure completely if you know the four quantum numbers, like principal quantum number, azimuthal quantum number, magnetic quantum number, and spin. Similarly, in solid, if you want to learn about electrons in a solid, you need to know these four quantities. And the interesting thing is that photo emission spectroscopy allows you to detect all the four quantities. So basically, you can actually learn everything that you need to know about a material by experiment. So this is the strength of this technique. Okay. So by determining all the four quantities in a solid. Okay. Now let's talk about what do we mean by this initial state and final state. Okay? So if I'm going a little bit technical in some aspect, you please stop me and ask me. Let's talk about this initial and final state, what is happening. Now, what we are doing is that we excite an electron which was there in a material by some photon energy, which is the energy is of the order of say 20 electrons. Normally, we use helium-1 light. So where you have a helium lamp which has an energy of 21.2 electron volt, you can have another light like 40 electron volt, or you can use an X-ray source, which depending on the kind of X-ray source you use, the energy is of the order of say 1,000 electron volt, or 2,000 or 10,000. So now you can see that the electron which was there at the initial state, like at some binding energy, so that energy get elevated by some say 1,000 electron. So if you go 1,000 electron volt above the Fermi level, the electrons are basically behave like a free electron because they are not really bound to the solid. So their energy spectrum is more like a continuous spectrum. So then you can see that the transition probability basically is determined by the initial state, how it overlaps with this free electron state in the final. Okay. So it gives an idea as if that your photoelectron spectrum is basically determined by the initial state. That's not actually correct. I'll try to correct it soon. But yeah, is there any question? Okay, so as if that the initial state is the most important thing. So I'll tell you one example where this kind of things actually is applicable. Look at this photo emission spectrum. Okay. So this is a valence band spectrum. Valence band spectrum means the highest occupied band. So any molecule, you can say the HOMO, you can say, because you know that you can do photo emission if it is occupied band electron. So if you have an unoccupied level, of course, photo emission is not relevant for this kind of state. So only relevance comes for the occupied level. So if you are doing say semiconductor, it's the valence band, or metal, it's a partially filled valence band, and so on. If you are doing photo emission from a molecule, it's the HOMO that I am looking at now. You can of course excite a whole level also. Now you can see that I have done this experiment with 3 different energies. One is 21.2 electron volt. This looks like this curve. If I do with 48.8 electron volt, the curve looks like this. And if I do say 1486.6 electron volt energy, the curve looks like this. So it's very, very different. The same object you are looking at it, it's like that you are looking at an object by different colored kind of specks, and the color that you see depends on the kind of color you have in your screen. Okay? So you don't know what is the actual color of the object. As long as you have no idea the technique that you are using, how much it influences your result. Okay? So to know that, so this matrix element actually is one important aspect that you have to see. Now, what we can do is that people have done calculations like if you have one kind of state, what would be the transition probability? For example, so this is a compound that we have looked at, is iridium oxide. So this valence band is constituted by iridium 5d electrons and oxygen 2d. So they are basically hybridized, and you get the electronic eigenstates, which is a linear combination of iridium D and oxygen. Okay. Now I can actually calculate what is the transition probability of an electron if it is there in iridium D. So that means if psi I is iridium D, I can find out the transition probability. If psi I is oxygen P, then I can find out the transition probability. From that, I can actually correlate why some peaks are stronger. Now, if you look at the table, I can give you a reference. There are many standard tables are available where you assume that the final state is the free electron-like states and initial states are different states. Now, depending on the energy of excitation, so you can actually excite different states up to a different sensitivity. For example, if you use X-ray source, the iridium 5d states becomes much stronger compared to oxygen P state. But if you are at 21.2 electron volt, then oxygen P state becomes much stronger compared to iridium 5d. Okay. Now you can see that if you look at this spectrum, this peak is very, very strong compared to this in XPS or X-ray photoelectron spectrum. So that way you can say that this one is dominated by oxygen 2p state. Okay. Similarly, this one is dominated by iridium 5d states. This one, you can see that oxygen P is there as well as iridium D is there. Here also you have oxygen P and iridium D. But you can see that the change of this intensity is much stronger here compared to change of this intensity that you have here. Now this peak and this peak, since both of them, they have strong iridium D states and oxygen P states, then you can easily say that both of them are contributing to these two peaks. Means that they must be the hybridized states of iridium 5d and oxygen P. Okay. So from that experiment, you can say that means that A is basically the bonding states. So here I have shown you that how the hybridization happens. For example, if you have two hydrogen atoms, so they can hybridize and give you a bonding state and an anti-bonding state. The bonding states has this state plus this state, and the anti-bonding state has this state minus this state. So that gives you a known. Okay. So here always the anti-bonding states comes at higher energy compared to the bonding states. Here also you can see that the bonding state of oxygen P and iridium D they come here at this kind of binding energy, which is 6 point something electron volt. 0 is your Fermi level, and this energy is the anti-bonding state. Another conclusion that you can draw here is that since this one changes much more significantly in intensity if you go to this energy compared to here, so that means that this one has much larger iridium D contribution compared to this. So you can actually, from this spectrum, you can draw this kind of energy diagram where oxygen P and iridium D, then they may not be at the same energy level. Because if they are at the same energy level, then their change should be similar. But that's not happening. So since this one is changing much stronger, so that means that this one has more contribution from this. So that means oxygen P and iridium P must be like this, and this is the antibonding and this is the bonding. And these states where you can see there is no D contribution because there is a D. So it must be only oxygen which are not bonded. So these are called oxygen non-bonding states. Okay. So that way you can actually learn about the bonding, anti-bonding, non-bonding in a material using photoemission. Just by using the matrix area. But as you know that this is not really the true picture of photoelectron spectroscopy. So I'll come to the next aspect of this. Because the photoemission basically is much more complex. Okay? So what is happening here, let's think the photoexcitation process in a slightly different way. Okay? Assume that before you have actually signed the material with some light, you have n electrons. So it can be 100 or 1000. Usually it's Avogadro number, so 10 raised to 23 number of electrons. So you have, so assume that that is represented by n. That's the ground state. Okay. Now, due to the absorption of one photon, the electron comes out of the material, leaving behind this n minus 1 electrons in the material. Okay. So what we are doing is that we detect the properties of these electrons, property in the sense that you find out what is the kinetic energy of this electron, what is the momentum of this electron, what is the spin of this electron, and then use the conservation law and relate this property to the property of this n minus 1 electron system that has been left behind. Because you know that before photoexcitation, of course, the system was in ground state. Okay? That's the lowest energy state. So, which is, unperturbed state, and you don't really worry about it so much. So that means whatever you are learning about this photoelectron actually is a reflection of the properties of the n minus 1 particle system left behind. Okay? And that is happening by, say, various conservation laws that we have talked about. So now you can see that this n minus 1 electron state that this electron has left behind need not be in the ground state because it's an excited state. You have excited the system by a photon. Okay, so it can be any of the excited state, like if you have a Hamiltonian that represents this n minus 1 particle system, so it can have a many eigenstates. For example, if n minus 1 particle system has say 5 excited states, the electron has every probability to leave behind this in any of the 5 excited states, and you actually get 5 peaks for the same excitation. Okay? So this is the beauty of this and the complexity of this material. Maybe if I try to draw it schematically, let's assume that you have n electrons in this solid, and you have perturbed, which has an energy which is the ground state, and you have perturbed the system by a photon, and you knocked out an electron, leaving behind this n minus 1 particle system. Now, if the energy of this n minus particle system is here, and the electron kinetic energy is here, or the excited state energy is here, so this actually sum of this energy basically is the photon energy that you used. Now it has a finite, it's a quantum mechanical system, so it has a finite probability of leaving this system at here instead of here. So if you leave this system at this energy, then for the energy conservation, this kinetic energy of this electron will not be that high. It will be slightly lower because some part of the energy has been used up by this to leave it at a higher energy. So then this energetics would look like this. You also can leave this system at this energy. So then the kinetic energy of the electron will be here. Basically, in every event, the sum of these two energy would be equal to the photon energy. Okay. Now you can see that since your system is a quantum mechanical system and you have probability of leaving the system in any of these states, so in your spectrum, you will have electrons of all the three energies. Okay. And you essentially land up getting three peaks instead of actually one peak that we have just talked about in one of the spectrum. So this is the reason actually the photoemission spectrum is called, it's derived by the final states, not really the initial state. Because initially it's in the ground state. Now if for certain material, for some system, these energy levels are not really at a different energy levels. I mean, they are very close to each other. Then you see that final state effect is very weak. Otherwise, actually, it's very, very strong. One example I can show you, it's a very, very interesting example, is a nickel oxide, for example. Anybody who has studied solid state physics and so on, I am showing here some compounds where nickel is in different kind of environment. Okay, look at NiO. NiO, where nickel and oxygen, they form like in rock salt structure. So you have like nickel at one side and oxygen at the other side. So now, if you have an electron at the nickel side, you can see that this electron can move in any direction via hopping. So you have an oxygen here, so electron can move in this direction. Electron can move in this direction also because you have an oxygen here. You can move also in this direction. So all in X, Y, and Z direction, electron can move. So this is the reason this material are more likely three-dimensional system. But look at this material, where say La2NiO4 or Pr2NiO4 or any kind of, so you can put a rare earth. So the structure is like this. So here, if you have an electron here, it can move to this direction because you have oxygen here and it creates a bridge. Similarly, it can move also in the Y direction because you have oxygen here. Now, if it wants to move in Z direction, there are problems. Because you have a nickel here and a oxygen here, but there is no nickel here. This is some lanthanum or something which is say 3+, it's an ionic kind of solid. So the electron has difficulty to move in this direction because you have a lanthanum and then there is a long gap, then there is another lanthanum, then it comes oxygen and then comes. So electron, if it wants to go from one nickel to another nickel, there is a lot of hurdle and there is no breeze that is created. That's the reason in this kind of system, the electron movement actually is confined in this direction or this direction, but it cannot go in this direction. So your material is a three-dimensional solid, but effectively the electronic structure is two-dimensional because it can move only in two directions. Now look at this material, Y2BaNiO5. Here you can see that the connectivity is even less because if you have an electron here, for example, this small thing, it can move in this direction, in the Y direction, but there is no way it can move in this direction or this direction. So the chains are looking like this, but they are not connected. You have a chain-like kind of system. So many chains are put together, but the chains are not connected strongly. So that way the electrons are moving actually in one direction. That's the reason these are called one-dimensional systems. So although the material that you see, always it has three dimensions, but from the electronic structure point of view or electronic properties point of view, they are basically one-dimensional systems. And this one is even more different because here you have an electron which is within this kind of this tetrahedra, which is the signed one. But this electron cannot escape from this tetrahedra because there is no direct link between them. So these are called zero-dimensional system. So although your material is three-dimensional because we see them, it has X and Y and Z direction, all the dimensions are there. But electrons actually are not mobile in all the directions. So depending on the connectivity, inside the structure. Okay, so the dimensionality depends. Now I have looked at nickel 2p core level, okay, from my experiment, and they are looking at here. So if it is nickel oxide, it looks like this. If it is a PR2 NiO5, it looks like this. If it is Y2K NiO5, so you can see that I have knocked out the electron from only one level, 2p level, but you have so many peaks. One here, another here, there is one here, there are few here, here there is one, this is one. So you can see there are so many peaks comes out. Not only that, the kind of environment you have put in, the features also looks very different. The relative intensities are different. For example, here, this one is quite strong in intensity, but in this case, this is very weak. So you can see that although you are knocking out electron from one level, it's not necessary that it has to be one peak, and also it's not necessary that peaks should be similar in every system. So this atomic description that we talk about is really not valid in solid. Okay. So this is a very, very important aspect, and always one has to keep in mind that whenever you are doing photo emission, you have to keep in mind that it's the spectral function or the photo emission spectra strongly depends on the kind of excitations you have. Okay. Now I'll go to the detection process, how we detect the electron and its momentum. This is your sample, and you have excited an electron by this photon. So now the electrons can emit from the sample in any direction because you have all possibilities are there. So what we do, we put a detector like this. So where this is an electrostatic lens, so where we try to focus the electron in this way, you can see that the red one is the electron which is emitted in this direction. The green one is the electron which is emitted in this direction, and the black is straight, normal emission. So we focus in such a way that the electron which has come out here, they can be put here on the detector. The electron which has come here, they can be put here in this direction. So that means your detector, different location, detects electron coming out at different angle. Okay? So what we do, if you use a single crystal and find out the electron kinetic energy, that is determined by this analyzer, and also you find out at which angle it comes out. That's the reason it's called angle resolved photoemission spectroscopy. Now, if you know at which angle it comes out, you know that the electron, when you are detecting, it's like a free electron. Its energy is p square by 2m, where p is the moment. And p can be expressed as h cross k. H cross is the Planck's constant h divided by 2 pi. So h cross square by k square by 2m. M is the mass of the electron. So when you know the kinetic energy, you know the momentum k, but momentum is a vector. You know, it has a direction. So for that, to know the direction, you need to know at which angle that it comes out. So once you know the direction of the electron that has come out, and you know its kinetic energy. So this can be used, this information can be used to find out what was its momentum before its excitation. Okay? So if you know the theta, you can easily find out. So I can find out, say, for example, K should be equal to square root of twice m. So you multiply 2m here. So 2m epsilon kinetic energy, take square root. It gives you the value of K. So this is root over twice m e kinetic energy. And then divide by h cross, that gives you the K. Okay. Now I can find out the parallel component, which is the sine theta, the K parallel. And for perpendicular component, it's not just the cos theta part, because when the electron comes out, it has to overcome a potential barrier. Okay? So when it comes out of the solid, which is called the inner potential. So if you consider that potential, then the perpendicular component looks like this. So this parallel component and the perpendicular component actually is the crystal reciprocal lattice momentum vector, okay? Or the reciprocal lattice vector. So that means the electron that you have detected here, if you know at which angle it comes out, you can find out what was its K value before its excitation. So you know the binding energy, you know the K, so you can actually plot energy as a function of K, which is the energy band dispersion. Okay, so that's the way you find out the energy bands. That's the reason this technique is called RPS, angle resolved photon spectroscopy. Okay. So now I'll go to different terminologies which are used. I'm sure all of you know about XPS. XPS is called X-ray photoelectron spectroscopy, where you have used X-rays to excite electron from various states. You can also call UPS. This is not uninterrupted power supply, but in spectroscopy it's called ultraviolet photoelectron spectroscopy, where you can use helium lamp or xenon lamp or anything else to excite electron. You can also use lasers, so like that. So then you call it laser photoemission spectroscopy. So these terminologies which are there, it depends on essentially the kind of light that you use for excitation. But the technique is basically same, photoelectron spectroscopy. So you can use synchrotron radiations. Synchrotrons has a many, the electrons are moving in a circle, and if you decelerate it, you actually emit electron energy, so which can vary from say low energy to very, very high energy. So you get a continuous steering of energy in a synchrotron. So that's then is called synchrotron radiation photoemission spectroscopy. Then soft X-ray photoemission spectroscopy. This is VUBPS. This is also ultraviolet, where you go to higher extreme ultraviolet range and so on. Then depending on the resolution, you can call it high resolution if the energy resolution is very high. Angle resolved photoemission, RPS, which is very much used by many people, spin resolved photoemission or spin polarized photoemission, you call it SRPS or SPPS. So these are the terminologies which are used. I think chemists and biologists, they use XPS very, very extensively, okay, to find out. So I'll give you one example of that. Before that, maybe it's here already. So for example, you want to learn, if you have a compound, for example, and you want to find out what is this compound about. Normally in chemistry, what we do, we can do different kind of titration and find out how much element is there of different kind and try to understand the composition. But XPS is a kind of a technique which allows you to detect, or find or determine the compound without going through this kind of destructive method where you have to destroy your sample to find out the composition. So if I do an experiment, this is a hard X-ray, like I have done an experiment using 6 kilo electron volt. And this is the plot, that's the Fermi energy, that's the highest occupied level, and you have many peaks. So how do I find out which are these peaks? Now the binding energy of an electron in various elements, they are extremely unique. For example, oxygen 1s has a binding energy of 532 electron volt. And at this energy, you often don't find any other kind of binding energy of any other element. So that way, these peaks are very element specific. So I can actually go to a table. For example, I know the peak positions. So I am showing you 3 elements, say calcium. 2s has a binding energy 430, then 2p has 356, and so on. So I know different binding energy which were calculated. You can determine also by experiment. Take a calcium and do the experiment and find out where it comes. So similarly, iron has different binding energies. Arsenic has different binding energy. From that, I can actually identify which are the peaks which are there. Okay. So now I know which are the elements are there in this compound, but I don't know how much amount is there. So to find out how much amount is there, what I can do, I can try to find out the area under the car, and then try to get an idea of what is happening. Or there are other methods which I can use. The 2 things which are mentioned here. One is that the first thing that I said, the amount of each element will depend on the intensity of the, which is area under the car weighted by photo emission cross section. Because when you are knocking out electron from a state, it's not necessary that it would be same for knocking out an electron from other electronic state. Okay, so you need to really find out the area and multiply by the photon emission process. But the problem is that you actually need to find out the energy range. For example, if I go to this peak, the iron 2P. Iron 2P has so many peaks, but you don't know really from where to where iron 2P actually is applicable. Is it from here to here, or it's from here to here? This energy, it's not very clear the energy. Not only that, you have a background which is contributing significantly, so you don't really know what is the area under the curve unless you subtract the background. And background function is actually one of the most complex thing to find out because you don't really know what the background function is. It strongly depends on the kind of excitations. So that means that you don't know the energy range, you don't know the background function, and most important thing is you don't even know the cross section because you know the cross section from atomic kind of calculations. But in solid, these things are different because in solid you will always have a solid state effect. Like if you have a other atom nearby, so then that will have a hybridization with these four levels. So the excitations will be different. But you can of course use some approximated method and try to find out how much is there. The other method you can use is that balance. You know that if a iron, for example, if it is in 2+ states, so knocking out an electron from a 2+, iron 2+, is different than if you knock out an electron from iron neutral kind of a state, iron 0 or iron 3+. Okay, so because if it has a higher valency, knocking out an electron will be more difficult. So the binding energy will be different. So if you know the binding energy from this kind of photon emission spectrum and correlate it to the valency of the element, then it's easy because you know the valency, then from that you can find out what is the composition. But then the materials are much more complex because you know that in many of the materials the valency is not really unique because you can have multiple valency. For example, Fe3O4, you have two kinds of iron 2+ and 3+ are there. So you don't know which ratio it is there. And often the energy difference between these 2+ and 3+ is not big enough that you can distinctly find out. So sometimes you have various broadening effects that keeps all these elements very close to each other. So it's not very easy to find out the valence. You have to do some kind of a fitting and always there are errors in that. So, and then of course if they are covalent materials, things are even more difficult because the valency is applicable when you have an ionicity, but covalency, I mean, it's very different. So all these kind of things, then of course the final state effects are there. You have, because of the final state effect, you have many peaks instead of one peak. So you don't even know that which peak corresponds to what valency. So there are complications. So to find out this composition, what you have to do, essentially people try to use both of these methods and try to see which one is the most suitable method to find out that. And I can actually find out this compound is calcium iron to arsenate 2 from this kind of analysis. So since you can actually find out a composition of a material using this X-ray photon emission spectroscopy, so this traditionally used to be called ESCA, electron spectroscopy for chemical analysis. And this is extensively used by chemists and biologists. Even now, I mean nowadays, even if you discover a new material and find out what is its valency or what is its composition, you just do XPS and try to find out. It's an extremely powerful technique. Okay? But we use this technique much beyond to learn the properties of material. Okay. So to do that, you need to know, of course, this is that escape depth of an electron that comes out. So here I have shown that if the electron kinetic energy is of some kind, so how well it comes out of a material. So that's the escape depth. This is a universal curve, and you can see that the escape depth is very small, something like say 10 angstrom or so, so 5 to 10 angstrom. So you look at something like 2 to 3 layers at this energy. If you are at a higher energy, it can be 20 to 40 angstrom or so. You can look at some more layers. At lower energy also, you can look at more layers. So you can see that the electron spectroscopy actually is a very, very surface sensitive technique because you are looking at only few top layers in a material. So it's extremely important that the material that you are studying is very clean because you are looking at only top few layers of this material. So if you want to make a spectrometer, what are the things which are important? So you need to have a ultra-high vacuum. So ultra-high vacuum means that it's of the order of say 10 raised to minus 14 atmosphere. So you know that, I mean, you have in standard atmospheric pressure, 22.4 liter has Avogadro number of molecules. So now you can see that if you go to this kind of vacuum, you reduce this number significantly. Normally, if you assume that, say, for example, oxygen, whatever is there, so if it hits a sample surface and it gets stuck, which is called sticking coefficient, if it is 1, it takes about 10 raised to minus 6 seconds to cover the whole sample surface by 1 layer. Okay? So that means that anything that you have in atmosphere, it's extremely dirty because you have carbon dioxide, oxygen, all kinds of materials. So if you do photo emission on this kind of material, what essentially you see is the signal from the top impurity layer, not from the material. So you need to have a clean material inside an ultra-high vacuum. So for this kind of experiment, you need to have a good vacuum system. And so that's very important. Vacuum technology is very important. And then you need to handle sample inside the ultra-high vacuum system. You need to have a facility to clean the system inside ultra-high vacuum system so that it remains clean for the duration of your experiment. Okay. A typical photo emission spectrum that we have designed here, you see, this is a machine that has been made using facilities in India. So we have companies which can make. So we have designed and given this design to the company and they built this. And so this is the machine that we have in our lab. This has an advantage that it, of course, you can build this kind of machine at a very low cost. And also, you know, in and out of this, if there is a problem, you can actually sort it out and so on. And of course, you promote the technology in our country. So after this company, they built our machine. So they have opened up a new company and now they are actually producing high quality materials, kind of chambers and so on, and they export. So this is an advantage of that got created by fabrication of this kind of machine. The one advantage or the speciality of this instrument is that the energy, okay, this is another machine that we have here. This is the spin resolved photo emission. So the advantage of this is that you can detect electrons with extremely high accuracy. So this is the best kind of accuracy that anybody has achieved so far. So the energy resolution is of the order of 1 million. So we are extremely happy about it that we could reach to this kind of energy accuracy that we detect in our spectroscopy. Okay. So and if you do XPS, of course, the resolution is little worse because you need to. I mean, it depends on the experimental condition. I don't want to talk about it much more. Okay. Now, I'll try to go to some examples. Yeah. So, I'll quickly show how one can actually learn various puzzling issues in a material using this technique. So far, what I have shown, the examples are where how you can do the chemical properties of a material, like valency, hybridization, you can identify a material. So those things that I have shown. Here I'll try to show the physical properties, how it can be determined and why this high resolution is so important. Okay? So anything where we do an experiment or any kind of research that we do, one thing that we need to keep in mind that the quality of our research has to be very high. Okay? Any data that we collect, the quality has to be high. Otherwise, doing that makes no sense. So I'll try to show you why this is so important. So this is one material where barium iridium oxide, BaIRO3. The structure is like this. So you have this kind of iridium oxygen kind of units. They are arranged in this kind of structure. So this is an orthorhombic structure, and in real system they are slightly tilted. So that means the electron actually can move in this direction, but it has difficulty to move in X and Y direction. So it can move only in Z direction. That's the reason it's a effective one-dimensional system. And the main problem of this material is that, of course, it's an insulator. Insulator means that if you increase temperature, its resistance goes down. Okay? So from the electronic structure point of view, you have a gap between the highest occupied level and the lowest unoccupied level, or between the valence band or conduction. In molecular picture, you can say that there is a energy gap between HOMO and LUMO. Okay? So similar kind of things in solid. So you have an energy gap between the valence band and conduction. Okay? Now, the problem with this material is that if you measure resistivity, okay, you see, we know Ohm's law. Ohm's law is that if you have pass a current through a material, the voltage actually that you have applied is proportional to the current that passes through it. So that means if you plot voltage as a function of current, you should get a linear dependence. So any plot that you have. So here I have applied a voltage and current, and if I plot, it shows a straight line kind of behavior at a higher temperature. But if you cool it down, you can see that, for example, at 120 Kelvin, it goes somewhat linear, but then here it shows non-linear. You see it as it goes down, so negative negative slope, which is very unusual. So which you don't really expect in any material. Okay? So why it is happening? It's an insulator. Normally you don't expect this kind of behavior. Some of the material where you can see this, if it is a metallic, like you have an electron density, finite electron density at the Fermi level, and they can show you some kind of a density of states, a density wave, like they arrange in a kind of a sinusoidal wave like of things at a very low temperature. So that can give you this kind of anomaly, because if you apply voltage, this density wave that you have created, that gets part up, and you get a conductivity. So this kind of anomalies or violation of Ohm's law often can happen in CDW kind of transition, or this non-linear kind of things in CDW, like charge density wave system. But this one is an insulator. There is no electron at the Fermi, so it cannot give you this kind of behavior. So we tried to look at it using spectroscopy. The kind of spectra explanation that I wanted to give you here for the density wave is like this. So if you have a solid, assume that this is a one-dimensional solid. Now you can have a distortion in a solid, so which changes the periodicity. So if you change the periodicity, the electronic structure changes. For example, you can see the electron density, if it was a uniform, it will be looking like this. This is called charge density wave. You can also have a spin density wave. That opens up a gap. So at room temperature, you have a normally metallic kind of band, and it opens up a gap at low temperature. And this kind of system can give you this kind of anomaly. Now, if you do high resolution spectroscopy, you can see that I have looked at the energy, the spectra close to the Fermi level, the highest occupied level. You can see, although it's an insulator, but you have some small density of states. This you could, determine only if your resolution is very, very high, of the order of say 1 millivolt. Is there any question? Okay, so I think I've taken quite a long time. So I'll try to quickly wind up with giving you some interesting examples. So what we are trying to say that although it's an insulator, so you can have insulator of different kind. One kind is that you have a gap between highest and lowest occupied states, between the valence band and conduction band. Or you can have an insulator where you have electrons at the Fermi level, or like metal, but they cannot move. So you have a localized electronic states. So here what is happening is that this is a special kind of insulator where you have electrons at the Fermi level, which was supposed to be moved, but somehow they are localized. And this scenario can give you a charge density wave kind of things, because you have now electrons at the Fermi level. and that can give you a density wave that gives you this kind of. So this is one kind of puzzle that you can solve. The other thing that I can talk about is, you say, nowadays many people have looked at nanomaterials, like say, many people have worked on various kinds, zinc oxide, for example, magnesium oxide. I know there is recently a book is written by Upenda and so on, so they must have talked about it. So you know that their electronic properties, the color of the material changes significantly if you go to a nanostructure. Like silver can look like gold if you go to a smaller size. Similarly, its magnetism also varies significantly. Normally we know that a material is magnetic only if it has a magnetic element like iron, cobalt, nickel, or say rare earths like say cerium, praseodymium, neodymium, gadolinium, like that. So any of the magnetic element you put in, then it can show magnetic behavior. But the funny thing is that many of these materials nowadays people found, they show ferromagnetism, but there is no magnetic element. So these are all examples. Professor Sena Rao has worked on many such materials. There are many kind of examples are there. I'll show you one example, calcium hexafluoride. Calcium is not a magnetic element. Boron is not a magnetic element. But if you do magnetization, you see that it shows a hysteresis. So it's very funny. And not only that, it's actually, the Curie temperature is very, very high. Something like say 600, 700 degrees centigrade. I mean, 700 Kelvin. So, so this is very unusual kind of thing. So we try to look at why it shows ferromagnetism, although it doesn't have a magnetic element. And the answer is given here. So normally, why do you see magnetism? So normally in a material, if the electrons are really mobile, they don't contribute in magnetism because the electron spin is visible at every side, so they are equally distributed. If you want to get magnetic moment, I mean their spin is visible, you need to make them localized, okay? Somehow. So you need to have some local electrons like these d electrons or f electrons. In rare earths, like if you look at the periodic table, the 4f, 5f block elements, or say 3d, 4d block elements, they have electrons which are localized. So, and the energy band is partially filled. So that can give you magnetic moment. Normally S and P block like alkaline earth or alkali material. So there the electrons are highly mobile. So they cannot give you magnetic moment. Here we show that even if you have say boron 2p electrons which are highly mobile, if you have a disorder, like if you have vacancy or impurity, that can give you localization of these electrons. So that gives you local moment. And that's the thing which is happening in this kind of materials. Like if you have, if you have a nanostructure where the surface of the nanoparticle is not really very, very pure, you have some defects or you have some impurity, that can localize electrons on the surface and give you magnetic field, and that gives you ferromagnetism. So this is one way of explaining why you see a non-magnetic element shows magnetism, behave like magnet. The other example that I talk about is topological insulator, which I also mentioned. We have been working on this. So topological insulators are one of the recent discoveries. Recent people have been working on extensively. So these insulators are normal insulator in the bulk, but at the surface, the electrons are mobile. So it behaves like metallic. And these electrons are not really a typical metal. Like if the electrons, if any of you want to know, I can explain you in more details. For example, if an electron moves in the right direction and if it has an upspin, the electron which is moving in the left direction must be having downspin. Okay, so this is this selection which is there, which is not there in normal. So this is the speciality. So this comes from time reversal symmetry. Like when you have a movie running in forward direction, now if you move this cassette in the reverse direction, the way it happens. So now the forward and reverse moving direction is identical. Then you call there is a time reversal symmetry. Similarly, here, if the forward direction moving, like the momentum when it's positive, if the spin is up, If the momentum is negative, the spin is also down. Okay. So if this is satisfied, then it's called a topological insulator. So in the bulk, you have a conduction band, valence band separated by a gap, but surface states show bands which looks like this linear dispersion and crossing each other at one point. So for the red one, it's a forward moving electron with upspin, and the blue one, which is backward moving electron with downspin. So this spin selection is there, and since it's a linear dispersion, this is called a Dirac. Okay? So the cone looks like this. So the energy dispersion of these electrons, they are like Dirac particle or relativistic particle. Relativistic particle means that their rest mass is almost zero. Okay, so those who have studied relativity know that the energy square equal to p square c square plus m0 square c to the power 4. So if you put this rest mass m0 0, then your energy square is p square c square. So energy is linear in p. So that's the thing which is happening. Then energy is linear in momentum. Okay, so that's the reason these are called Dirac particles. They are not really the typical normal fermion. So they are called Dirac fermions. Okay. So these surface electrons. So this is the speciality of topological insulator. Nowadays, people are trying to get superconductivity in this kind of material, like the Dirac fermion showing superconductivity. This is an open question which is happening. People are studying extensively. We are also trying to look at it. And the speciality of this technique is that this is the only technique by which you can find out whether a material is topological insulator or not. Like Bi2AC3, the structure is like this. I'm not going into the details. This is the surface state, and they show like a Dirac cone. And if you find out the spin, this one has upspin, so then this one is downspin. And this is the bulk states showing a gap. So you have a surface state showing Dirac cone in between the gap. Okay. Now what you do? You can put say strontium or copper intercalation and make it superconducting and see if this superconductivity is related to the Dirac fermions. So this has not been proved so far. If you are able to find a topological superconductor, then of course it's a huge thing for boost our technology, like quantum computation, as well as various other things that people have talked about. Majorana fermions, you can realize. So I mean, there are a lot of things that can happen. I think since there is time is I've crossed already quite a bit, I'll just go quickly to other aspect of topological insulator, for example. You know, I mean, graphene has been studied extensively. Remember that there also you get the energy bands, which is like a Dirac cone, and the electrons are massless particle, but they are not topological insulator. So having a Dirac cone does not ensure that it's a topological insulator. It must have a time reversal symmetry satisfied, or say crystal symmetry satisfied, mirror symmetry, for example, which are called topological crystalline insulator. So nowadays what people are doing is that you have a topological insulator, it's a Di2AC3. Now you can put some magnetic element and make it ferromagnetic, the surface. So the moment you make it ferromagnetic, you can see that this time reversal symmetry is no more maintained, because you have both this band and this band which has same spin. Okay, spin has to be reversed if you have to have a time reversal symmetry. So in this kind of situation, you open up a gap. So now what you are doing is that you have a massless Dirac particles, and because of this perturbation, you actually create a mass into this fermion. So these are called massive Dirac particles. Okay. So that way, a lot of people are working in this kind of direction. So many materials which are studied. So now, you know, there are quantum wells people have been studying, like if you have a two-dimensional system. Upenda, how much time I can talk more?
So you can take another 2 or 3 minutes.
2-3 minutes. So okay. Fine. So then maybe I'll just close this, because I have quite a few techniques. I will give quite a few examples. I'm not going into all those details. Okay. Maybe I'll stop in this. Okay. Here I am talking about the quantum wells. You know, a lot of people are working on quantum wells. So what you do is that you take a glass and then make a thin film. So then the electrons within the thin film, they cannot get into the glass because there is a large energy gap in the glass, and they also cannot escape into the air. So these thin films ensure the electrons are confined within the two dimensions. Okay. So this is kind of a confinement. These are called quantum wells. But you can have a special quantum well which is here. So you take a copper and then put a cobalt layer, and on top you form a copper layer. So what is this cobalt does? Cobalt has a magnetic moment. So it means that the number of upspin and number of downspin is different because it has a moment. Okay. So now you can see that if you make a copper overlayer, these electrons in copper, where you have 10 electrons in the E band, so the upspin can actually connect to this cobalt layer. So this is not completely confined, but the downspin cannot connect because downspin is not completely free. So there is a gap. So you have a confinement effect for both weak and strong confinement. Strong confinement is here where the electrons are confined within this layer and they are not linked to anywhere, up and down. And weak confinement means the electrons are limited here. They can link to this, but they are not able to escape. And you can see from experiment, those who have studied quantum wells, you know that you have a potential well and solve, you have a ground state, first excited state, and second excited state. And if you do experiment, you actually beautifully see them. So you change the thickness of the copper layer and you can see the quantum well energy changes and different levels quantum well states you can see. And if you do spin resolved photoemission and identify them, you can see that for upspin there is no quantum wave, for downspin there is quantum wave. Okay? So it means that the confinement for downspin is ensured, but upspin doesn't show any confinement because they are linked. So they are weakly confined in this system. Like that, so there are many, works have been going on iron-based superconductors. So that also we have been working on quite extensively. I think I won't go into the details of this more. Maybe I'll just say one thing in this iron-based system is that so you can do time-resolved photoemission to find out that what is the lifetime of these electrons when you have excited. Okay, and that gives you an interesting information. So which we have recently discovered. This technique, although time-resolved photoemission has been done by many groups, but our discovery is that if you use polarized light, you can actually selectively excite electrons from different orbitals that we have shown here. So, for example, if you use one kind of polarization, you can excite electrons of one type, which has a lifetime of the order of, say, 2 picoseconds, so 2000 femtosecond. And if you use another polarization, you can excite another electrons. Like here you have DXZ and DYZ electrons we excite selectively. It has a lifetime of the order of 600 femtosecond. But if you excite DXY electrons by using a polarization, suitably chosen polarization, then it has a much stronger lifetime. So from that, you can actually tell us, which electron actually take part in what kind of properties of a system. This has been a big concern by the community because, any material, so you have a insulator, you dope some electron or hole, it becomes superconductor. Now, when you dope electron or hole, you also change the chemical environment. You introduce some disorder, some defects, some impurity, and at the same time you are changing the electron concentration. So you don't know which one is really taking part in what kind of behavior. Sometimes these iron-based systems are much more complex because normally we know superconductors, they are not magnetic. Okay, so ferromagnetism and superconductivity is not really going side by side. So, but many materials show magnetic order and superconductivity at the same time. So how can it happen? So now we can actually use this technique and find out which electron takes part in what kind of behavior, whether these various properties are linked or not. That is something that one can find out using this. So thank you. for your attention. Maybe I can take some questions if you have. Okay. So should I disconnect?
No. Kalobaran.
No.
Professor Maiti.
Yeah.
Okay. Now let us thank the speaker for his beautiful presentation, starting from the very basic to the quantum level, how to probe the structure inside the bulk with the help of modern experimental technique. He has presented that. For that, we thank the speaker for enlightening us. Now, we'll switch over to the question answer session. Participants, already in the chat box, you have to write the questions. Our teachers are there. They will take those questions, will place to the speaker, and speaker will answer them. Now, I switch over to Professor Joydeep Mitro and Professor Joyita Chaudhary.
Sir, can you hear me?
Yes, please. Yes.
Okay. So I am taking a few questions from the YouTube live chat box. Okay, I am reading out. Okay.
Okay.
One question from Dr. Shaumen Ghosh. How does the XPS spectra work for a faulty structure? Because different kind of faults are quite natural in a crystal system.
Yes. So if you have faulty structure, like if you have a defect or if you have an impurity or disorder or something like that, so wherever there is a fault in a solid, so that changes the local or effective potential at that site. Okay. So if you have a structure which is faulty, the effective medullum potential in a material will be different. Okay. So the electron which are emitted from a faulty site will be different from the electron which is emitted from a normal site, okay, in the material. So you are looking at the XPS spectrum, if you see multiple peaks, so that means that the electrons that is coming out from different sites, they are not equivalent. Okay. So there might be some faults are there. So from that you can find out actually whether there are faults. So you basically look at how many peaks are there and what is the width of the peak. Sometimes what happens that the width of a peak actually becomes larger if you have faults. Okay. So from the width of the peak or the number of peaks that you see, from that you can find out whether there are faults in a material. So this is quite effectively done by experiment.
Okay.
Is that okay?
Another question from Niladri Ganguly. What are the advantages of electron microscopy over super resolution optical microscope? As you know, it would be invasive to sensitive sample.
Okay, so microscopy basically is different from the thing that I have talked today, but I can take this question. Normally, you know that if you want to have an atomic resolution, like you want to really view the atomic picture, then you need to have electron microscopy because your effective wavelength has to be smaller than the lattice constant. Normally, if you use, say, light, you can do imaging by using light and try to do a microscopy. But then that will basically require a very, very high energy light. Okay? So normally electron microscopy is very good. Nowadays, very high resolution tunneling electron microscopy TEMs are there, by which you can get the picture of like the image of a material with atomic resolution. The resolution can be of the order of an angstrom or less than an angstrom. Normally, you know that in a material, the lattice constant is of the order of say 1.5 angstrom or so, the bond length between two atoms. So whenever you want to find out the atomic picture or image, you need to have a probe where the effective or characteristic wavelength is smaller than that, like 1 angstrom or lower. So electron microscopy is much easier a probe, I mean, where the effective length, the T-Broglie wavelength of an electron is smaller. So optical, imaging can be done, but it's not really so good or so efficient in this matter. So if you want to get a microscopic picture or image of a material, it's good to use electron microscope.
Next, sir, I am reading the question of Shubhayu Roy. For the capital J versus capital E plot at 120 Kelvin, there were multiple values for the same E at the non-ohmic region. How is that detected in an experiment, the different values at same E?
It's a very interesting question. So what happens is that normally, so what is actually happening, I have been thinking about it. For example, you are doing experiment at say 120 Kelvin or 130 Kelvin. So you increase the voltage and you find out how much current is passing through it. Now, beyond a certain voltage, what happens is that the current that passing through it becomes higher, but the potential drop across the material, although you have increased the voltage, but the potential drop across the material is lower because the effective resistance becomes lower. Okay, so this happens, this kind of material in these materials, because of this application of higher voltage, it disturbs this charge density wave state or spin density wave state. So when you have a density wave states like CDW or SDW, beyond a certain voltage that you apply, so then the impedance in a material reduces. So what we measure is basically the potential drop across the material. So you apply a voltage across the material, but whatever you have applied, it's not necessary that that's the same voltage will be the potential drop across the material. So beyond a certain voltage, the potential drop across the material becomes lower, although the current becomes higher, because this higher voltage actually disturbs this CDW or SDW kind of states. So that gives you a point which is above a point which was reached at a much lower voltage. So that's the reason you get multiple points. So it's not that multiple points are obtained at a particular voltage. You apply a voltage, get a current, increase the voltage, get another current. But what happens is that beyond a certain voltage, again, the resistivity goes down because this potential perturbs this density wave states. Okay? And you get a higher current, but the potential drop becomes lower. So that's the explanation of negative drop of negative resistance that you get. So this is a speciality of this kind of physics. Now if you increase temperature, then of course the curve becomes different. And if you are above a temperature where this density of states is not there, you don't have this anomalous behavior. Okay, is that clear?
Okay, sir. Next question is from Ronak Sen. Auger electron spectroscopy is better than XPS?
Sorry?
Is Auger electron spectroscopy is better than XPS?
Which electron spectroscopy? Sorry, I didn't.
Auger, AUGER.
Oh, OJ, okay, sorry. Okay, I call it OJ. Okay, yeah. I mean, we AUGER OJ. Sometimes we will call it auger, but we normally pronounce it as OJ electron spectroscopy. Yeah. Okay, so the electron spectroscopy, basically, I have not talked about OJ electron spectroscopy. So photoelectron spectroscopy that we are doing, XPS or UPS or RPS, what we do is that a electron absorbs photon and comes out of the material, and we try to find out how many electrons came out at what energy. Okay, so that's the photoelectron. It reflects or represents the density of states. Now in OJ electron spectroscopy, what happens? So for example, you knock out an electron from a core level. So say for example, say oxygen 1s level. Now one electron from say oxygen 2p, it fills up this core level, and this energy for transition of oxygen 2p to 1s is used up to knock out another electron from the 2p. Okay, so that means that in initial state you have a hole in the 1s level that creates two holes in the valence band or 2p level. It can be 2p level or it can be any other level. So this is called the OJ process. Now OJ process gives you a picture where you have two holes. Okay. So this is not the simple density of states. So what you have to do is that you have to convolute the density of states with itself if you have both the holes at the same level, or if you have both the holes at different level, then you have to actually convolute one of the density of states with the other to get the spectral function. So OJ electron spectrum is not a simple representation of density of states. It's a representation of joint density of states up to, convoluted to density of states. So that way, it's more complex to understand, and it's not really give you the electronic structure as such, but you can get additional information like if you have two holes, then what happens? Like electron interaction parameters can be extracted and so on. So, if you want to identify an element, of course, OJ electron field spectroscopy can be used instead of XPS also, because those are coming at a specific energies. So there is no special advantage in that. But otherwise, if you want to get a simple density of states, it's better to use photo emission spectrum like XPS or UPS instead of OJ spectrum, because that represents the joint density of states of two holes. Okay.
Okay, sir.
Yeah.
Okay. So is there any
Next
question,
question
Jyotika?
from yes, sir. For one, then Jyoti will read out some.
Yeah, you can raise any number of questions.
Okay, sir. From Choyan Patro, for linear dispersion relations, if we calculate the electron effective mass, it becomes infinite. Then why do we call them massless Dirac fermions? Which mass are we referring to here?
Yes. So this is the thing which I also mentioned briefly. You know that if the electron velocity, effective velocity is low, then we don't call them Dirac particles. The relativity comes into the picture. Of course, whenever you are talking about spins and so on, you need to talk about the relativistic picture. Okay? But normally for the band dispersion, where you are talking about the momentum of a electron, so if the velocity, effective velocity is not very high, we normally call them normal electrons, not really Dirac particles. Okay. Now, if the energy is very high, then instead of using normal energy momentum relation, you use Dirac equation. So Dirac relation, which is if the energy of an electron is E, like kinetic energy. So the Dirac equation says that E square equal to P square C square, where P is the momentum, C is the velocity of light, plus m0 square C to the power 4. Okay. So the energy square equal to momentum square multiplied by velocity of light square plus m0 square and C to the power 4. Now this m0 is called the rest mass of the particle. Okay. So when P equal to 0, you get the effective, inertia, which is m0. Okay. Now, in case of Dirac fermions, if you put m0 equal to 0, the rest mass equal to 0, then the relation comes out as E square equal to P square C square, where C is a constant. So that means E equal to P into C. So the kinetic energy is linearly dependent on momentum. Okay. So this means that whenever you have a linear dispersion, means that energy and as a function of momentum gives you a linear plot, you call that the rest mass of the particle is 0. Because in a relativistic description, if you make m0 equal to 0, you get this kind of relation. Okay. So that's the thing. Then you cannot determine the effective momentum or inertia just by simply using solid state rules like this d2e dk square or something like that. So normally if you have a normal Schrodinger electron or in a solid, so you have the energy dispersion and you can find out effective mass. So by taking double derivative, which is not possible when you have a linear dispersion, because the relations are very different. Okay. So here the linear dispersion mass phase particle means the rest mass is zero. Yeah.
Okay. Now over to Joydeep Mitro. He will read questions from Google Meet.
Yes, please.
Okay, am I audible, sir?
Yes.
Okay. So there are a few questions from Google Meet. One is by Prof. Jana. She has asked the question that for an unknown material like alloy, how to start this kind of process? What are the parameters we should control?
How to start?
How to start for an unknown material?
Yeah.
How to start with the unknown material?
Yeah. So that's the thing which I mentioned when I was determining when I was trying to identify material. So XPS is an extremely good technique for that. I mean, this is probably the best technique as far as I know. So you have an unknown material, you just get a XPS spectrum and find out the peak positions. So you'll get a multiple peaks. So find out the peak position. Now, you know that when you have like for example, if you have oxygen, then you will always get a peak at 530 EV binding energy. So you find out the binding energy of each of the every peak and then correlate this. It matches with which kind of core level emission of a particular element. And this can be uniquely determined. For example, you can have another say core level which is close to 530. But then those material will have another core level which is at a different binding energy. Like if you have only a peak at 530, then you are sure that there is oxygen in this. For example, if you have a peak at say 280 electron volt, then you are sure that you have a carbon in the material like that. So the elements you can easily find out just by binding energy of the peak. So once you find out the element, the major part of the thing is done. So you know which are the elements which are there in your material, but make sure that your sample is clean because oxygen and carbon can come from the atmosphere and it can contaminate the surface. So when you are doing an experiment, usually you put the sample in ultra-high vacuum chamber and then clean it inside, like take it inside, expose a clean surface and do the experiment. Once you do that experiment, whatever peaks you get, from that you can associate the binding energy of the peak to a particular emission from an element, and you identify the elements which are there. So this is the first thing. Like when you make a material, if you want to determine structure, you do a X-ray diffraction pattern, outer X-ray diffraction, and then assign the peaks to different planes. So here you assign the peaks to different emission of the core levels and find out the elements. And then you find out how much amount is there. That there are two methods that I have showed. One is that you can find out the area under the peak and then multiply with the photoemission cross section for that energy, and then take the relative ratio. That gives you the relative ratio of the amount of elements that are there. Like if you have say silicon germanium alloy or say iron chromium alloy, so like steel or any other material. So you know that iron is there, chromium is there, nickel is there. Then from the peak area, you find out how much amount of iron, chromium and nickel is there. And from that, you can find out the composition. So basically, XPS is an extremely good technique to find out what is the composition.
Okay, sir. Next is from Devayan Chatterjee. He asked that why kinetic energy of photoelectron energies depends on the chemical environment in case of XPS.
Yes. So when you are doing XPS, what you are doing is that you are knocking out an electron from a particular site. Okay. Now, if, for example, you are knocking out an electron from nickel. Now, if it is just a nickel, the effective potential at nickel side, whatever you will have, if you surround this nickel side by say 6 oxygen and form a octahedron, the effective valency at nickel side will be different because oxygens are negatively charged particle, and they will, because your element is neutral, charge neutral, so they will create effective positive charge, at the nickel side. Now, if your nickel has a positive charge compared to the neutral atom, so knocking out an electron will be more difficult because the positive charge will try to attract the electron cloud towards the nucleus. So, for example, like if you have say nickel 0 and nickel 2 plus, so the orbital radius also becomes smaller for nickel 2 plus because the nucleus, it will try to attract the electron cloud towards the nucleus, so the effective radius becomes lower and the binding energy of the electron becomes higher. So the electron kinetic energy will be different if your effective potential at the photoemission site is different. That's the reason actually it depends on the environment. It's very, very sensitive to the environment when you are knocking out an electron.
Okay, sir. Next one is from Atish Chakraborty. He asked that how to get density of states from the intensity distribution of photoelectron.
Okay. So, as I said that in that expression, the intensity of photoelectron is a function of density of states multiplied by the resolution function, the photoemission cross-section, and the lifetime broadening function. And then, of course, there is this surface sensitivity which comes into the picture. So what you do is that normally the resolution function is nothing but a Gaussian broadening. So like if you have a density of states, so if you just convolute with a Gaussian function representing your resolution broadening, so that gives you the final spectral function. Now if you have an experiment where the resolution broadening is very small, like say when we have a high resolution photoemission where the resolution function is say 1 millielectron, so it's like no broadening as yet. So then you don't really need to worry about the resolution broadening. Now the lifetime broadening is an important factor. So that gives you Lorentzian broadening to your density of states. So that you cannot avoid. Now if you are talking about density of states close to the Fermi level, like close to the highest occupied level, then the lifetime is very large. Like if you create a hole at the Fermi level, there is no electron above it to destroy this. So hole can live for longer. But if you are at a higher binding energy, then you have electron to destroy this hole at a higher energy. So that way the lifetime becomes different. So what you do is that if you have a density of states, I like take a model density of states, convolute with a Lorentzian which is energy dependent, and just convolute with the Gaussian and see if it represents your experimental spectrum. So if you find it, then you can say that the density of states that you have taken is actually a representation of your photoemission spectrum or electronic spectrum. Sometimes if you do a high resolution spectrum close to the Fermi level, you can use that raw spectrum itself as a representation of the density of states multiplied by Fermi-Dirac function. Because Fermi-Dirac function, of course, you have to always multiply because you are looking at the occupied part of the density. Okay. So that's the way you can find out density of states. There are other methods like what you can do is that you can symmetrize. So many people do, like you have a function as a function of energy and plot the same function as a function of negative energy, like plot it opposite, add them together. So if you add them together, then your Fermi-Dirac function, it's a symmetric function with respect to Fermi level. So if you add the symmetrized Fermi-Dirac function gives you 1. So that means that if your photoemission spectrum, you symmetrize, like you plot it oppositely and add them together, that actually gives you a density of states. Okay. But there are of course difficulties. So many people use symmetrized function, many people just divide by Fermi function. Or, you can just take a model function and multiply by Fermi-Dirac function and get a density of states. So these are the methods which are used.
Okay, sir. Next one, I'll just read out 2 more. Okay?
Yes.
So 2 more questions will be there. One is from Kaustubh Chakraborty. He asked that surface atoms have very different kind of environment than the atoms in the bulk. So in experiments, how exactly do you eliminate this kind of effect and extract the information from the bulk?
Yes, so this is one thing which I have also worked extensively. So basically what you do, I have shown a car where you plot the escape depth of an electron as a function of kinetic energy of the electron. So you basically know that at certain energy, the technique is surface sensitive, and you can increase bulk sensitivity by changing the photon energy that you use. For example, if you look at the valence band spectrum at say using a photon energy of 40 electron volt, where the technique is very surface sensitive, and then you look at the same spectrum using say 1.5 keV photon, where the surface technique is bulk sensitive, and then compare these two, where you have two different sensitivities, and you can extract surface and bulk. There is no other method you can find out, no other experiment you can find out surface and bulk separately. So this is the only way. I mean, you take series of spectrum at different surface sensitivity, and then extract surface and bulk from this.
Last one is from Dibbashankar Das, who asked us, you have shown an oscillation in chromophore spectra. What does it actually signify?
Oscillations?
In a probe spectrum, chromophore spectrum, PUMO.
Sorry, which spectrum?
Yes, written chromophore, PUMO.
PUMO?
Yeah.
I didn't get oscillation. You are talking about the time resolved spectrum, or? Oh, I see. Palm probe. Okay. Sorry.
Palm probe, yeah.
Palm probe experiment. Yeah. Okay. Now I understand. Yeah. So when you do a palm probe experiment, so what you do is that's the time resolved spectroscopy. Okay. I understand. So what you do is that you use one photon to excite the system, and then look at the electronic structure at a different time delay. So these oscillations that you are seeing is actually the atomic vibrations. So when you have a lattice, you know that at a particular temperature, there are vibrations. So for example, say any oxide, say carbon dioxide. So carbon and oxygen, they are vibrating with each other. So if that oxygen and carbon come closer to each other, the hybridization becomes stronger. So the electronic structure is different. The Fermi energy becomes different. When they go away from each other because of the oscillation, then the hybridization becomes weaker and the Fermi level changes. So that gives you the oscillation in your spectrum. So basically those oscillations directly tells you how the atoms are vibrating in a material. So this is the one interesting thing. So it's a real time picture of the vibrations. And from that time difference between different oscillations, you can find out the period of oscillation. And then you can also find out the energy because you know the frequency. So like if you have a phonon mode, like phonon oscillation, so what is the frequency at which it's oscillating? From that you can just find out H nu and gives you the energy of the phonons. So this basically involves the oscillation of the atoms inside the solid.
Okay, and the last one is just a minute. Last one is not a question. One request from Professor Sushanta Sen that could you please suggest some reference textbooks on this of electron spectroscopy, from where we can study and learn this data interpretation and this.
You see, there is a book by Stefan Hufner, but there are one or two books which are there. The most used one is Hufner, photoelectron spectroscopy. So if you look at photoelectron spectroscopy, give a search, you will find Hufner. So which is the most recent one. But I can tell you that whatever I have talked today about the photoemission technique, okay, none of this will be available in any of the textbook because these are the understanding of the research that has happened during last few years, and you will not find in a textbook. So there is no textbook. So for example, the final state effect that I have talked about, or the initial state effect that I have talked about in the initial part, the photoemission technique itself. So one has to write a book. There is no book available which tells you in detail. Even the surface effect that I have talked about, these are not, you may get some basic info in this book, Hupnar or few other photoemission books. But whatever I have talked today, these are actually the recent knowledge which has not been available in any book. So I have been thinking of writing one, but has not got time to do it. But for a basic, you can look at this Hupnar. I mean, it gives some idea, but there are some informations which are given it are wrong, because people, till that time, whatever they understood, they try to put it in a book. But I don't think the photoemission spectroscopy is really well represented in a textbook so far.
Okay, so thank you for that question answer, sir. So over to you.
Okay, thank you.
Thank you, Professor Maiti. Now only two questions. One,
yes, please.
Shall I share your email to those participants whose questions we are unable to answer?
Yes, you can share. I'll be very happy to answer.
Okay, thank you. So now I ask Professor Shatadal Bhattacharya to present vote of thanks.
Respected principal. Hello.
শোনা যাচ্ছে.
Respected principal ma'am, Dr. Ropita Mukherjee, Vice Principal Dr. Subrotin Das, Dr. Somdat Bhattacharya, Coordinator IQAC, and respected speaker, Professor Kalobaran Maiti, and the head of the Department of Physics, Dr. Uyedward. First of all, on behalf of Physics Department, I would like to convey our heartiest thanks to our distinguished speaker, Professor Kalobaran Maiti of TIFR, for making this excellent presentation of electron spectroscopy from undergraduate point of view. Professor Maiti has highlighted the role of electron spectroscopy to study different aspects of materials such as superconductivity, magnetism, etc. I hope the students across the globe must be benefited from this interesting and illuminative discussion. Thank you, sir, very much for making this event successful and meaningful. I would like to extend a special thanks to our principal, Dr. Ropita Mukherjee, for her guidance and inspiration. I would also like to thank our Vice Principal, Dr. Subrotin Das, for his moral support and cooperation. I would also like to thank the IQAC coordinator, Dr. Somdat Bhattacharya, for his cooperation and support. I am really happy to thank our head of the department, Dr. Uyedward, and other staff members of this department who have made this seminar a grand success. Finally, I heartily thank our participants from different parts of India and abroad for making this event a grand success. Thank you for your cooperation, as no event can be successful without any collective effort. So I extend my big thanks to all the staff members, both teaching and non-teaching of the college, for their cooperation. Once again, I thank you all for your cordial cooperation. Thank you, sir. Thank you.
Thank you very much. Thanks.
So with permission, I conclude our webinar. I thank Kalobaran again and all the staff, registered participants, etc.
It was my pleasure. Thanks a lot. Thanks a lot. I'm extremely happy. So at some point, maybe I'll come to Scottish Church at some point.
Sure.
Okay, bye-bye.
Bye-bye. Bye-bye.